Okay, so now we come to sort of an important part of the introductory material where we talk about two important classes of sequences. So two fundamental classes of sequences. And we'll consider them, of signals. We'll consider them in turn. This will be true both in discrete time and continuous time. So the first class is going to consist of the unit impulse signals and a related class of signals which we'll call step signals, but I think I'll just stick with the unit impulse signals. In continuous time, it'll be denoted by delta of t, so you might be familiar with the Dirac delta function from some of your other courses. And in discrete time, you may not have seen it, there'll be an analogous delta of n. And the second class is going to be the class of complex exponential signals. And there we'll be dealing with, in continuous time, signals that look like some complex number times e to the at, where both, so c is going to be complex and the exponent is going to be complex. And in discrete time, we'll be looking at something that's kind of similar. I'll write it, we'll end up kind of representing it slightly differently, but in essence, it's the same setup, except now we're looking at discrete time, not continuous time. So again, c and a, the constant coefficient in front, and the exponent are both taken to be complex numbers. Now, the reason we're interested in these is because we're going to be looking at, so why are these useful? And the reason is because we can represent lots and lots of general signals as linear combinations of these signals and some variations on them. So in particular, in this case, you should think of delta of t in terms of its possible time shifts as well. So the key point is we can represent lots of useful signals. And in some sense, we're going to see that we can represent essentially almost, I won't say all, but many, many, even you could say most of the signals that you might be interested in practice as linear combinations of such signals. And the reason that's going to be important, why do we care about linear combinations? Well, we're going to be dealing with linear systems, and the property of linear systems is that when you put in a linear combination of signals into the system, what you get out is a similar linear combination of signals that would be produced if you put each of those individual signals into the system. So in other words, linear combinations become linear combinations. And that turns out to be a very, very useful property for understanding what that system is doing to the signals that you put into it. So let's look at the discrete time unit impulse, and I'm going to look at its related signal, unit step. Okay? So the unit impulse is defined as follows. It's given by the following description. Delta of n is equal to 1 at time n equals 0 and 0 everywhere else. So if you wanted to draw a picture of it, it's a very easy thing to sketch and to visualize. At 0, it has magnitude 1, amplitude 1, and then it has 0 everywhere else. And so, if we want to indicate, we'll just put dot, dot, dot. It's going to continue with zeros for all times above and below that. So the unit step is given by the following definition. U of n is equal to 1 for n greater than or equal to 0. So the signal steps up at n equals 0, and it's 0 for n less than 0. So if you draw a sketch of that, it'll look like this. It'll be 1, 1, 1, 1, and so on forever. And then here, to the left of 0, it's all zeros. So clearly you would expect that there are some relationships between these signals. We can possibly even describe one in terms of the other. So let's look at some ways to express the unit step in terms of the unit impulse. Well, one way I could get it is I could take the unit impulse and then I could shift it one to the right, shift the unit impulse to the right, and then add those two things up. That would give me two ones at 0 and 1. Then I could shift the unit impulse by 2 and add that in. And so I can kind of get one stem at a time by adding shifts of the unit impulse. So I'm going to take delta of n. I'm going to shift it to the right by k, where k is going to be, well, I want to have all of the shifts that start with the 0 shift, just the original signal, and then every integer shift after that. So that's one way I can describe the unit step as an infinite sum of time-shifted impulses. Now, I can also do something that involves just a simple relationship between delta of n and u of n, but where I sort of flip the order. I want to express delta of n in terms of u of n. You can kind of get it by staring at this, or you can get it by staring at this picture. I want to somehow isolate one of those stems at 0. So I can also write delta of n as u of n. Now, what do I do to get rid of all of the stems except 0? Well, I could shift this thing to the right by 1 and then subtract. So you can also see that by looking at this formula. So I get that delta of n is u of n minus 1. Now there's another relationship that I want to extract to give us another way of thinking about the relationship between the unit step and the unit impulse. And for that, what I'm going to do is I'm going to introduce a change of variable. So I'm going to let L equal n minus k. And this is going to become delta of L. Now, when k goes from 0 to infinity, right, we can see what n minus k does. So in particular, when I look at what L looks like as I let k go from 0 to infinity, well, when k is 0, L is equal to n. When k is 1, L is equal to n minus 1, and then n minus 2, all the way to n minus infinity. So my L value is actually going to run from minus infinity up to n. So this thing we thought of as a sum of time-shifted impulses. But what is this thing equal to? I mean, how can we visualize this? Here, L is sort of the time variable, and we're summing up from minus infinity, L equals minus infinity up to n. You can sort of think of this as a discrete time integration, right? What I'm really doing here is I'm taking the dt integral, which is really just the sum, of a unit impulse signal from minus infinity to n. So if you think about what that means, let me try to help you visualize that. This thing is easy to visualize, the sum of time-shifted impulses. This one you have to think about a little bit. Let's look at the L-axis. Here's my impulse. And now what it tells me, if I want to figure out what the unit step is, the value of it at time n, I should take the sum from minus infinity up to n. Well, where's n? Well, n could be over here. N could be less than 0. What happens when I sum up the values of that unit impulse signal, delta of L, from minus infinity to n? I get 0. I'm just adding up all zeros. And that's good because u of n should be 0 when n is less than 0. What happens when n happens to be exactly 0? Then I add up a whole bunch of zeros from minus infinity up to here, and then I get 1. So u of 0 should be 1, and that's exactly what we want it to be. I should have indicated the height here. Right, so these are all height 1. What happens when n is positive? Well, I add up all of these zeros and the 1, and then a few more zeros. So the sum of all those things is still going to be 1. So when n is positive, I'm going to get 1 also. Okay, so that's another way of thinking about how the unit impulse and the unit step are related. Now, there's another interesting way to write the unit step in terms of the unit impulse. It's related to that. It's related to this representation here as a semi-infinite sum of time-shifted impulses. So here's another representation. And this one is going to turn out to be an example of a very general representation that we can extend to arbitrary signals. And what looks like is this. U of n, well, we said that U of n is the sum from k equals 0 to infinity of delta of n minus k. Suppose I would like my sum to go from minus infinity to infinity. Well, we know that for the terms delta of n minus k, where k is non-negative, we want a 1 in front. But for those terms where k is negative, we don't really want that term in there. We want it to be a 0 in front. So the question is, can we think of some function of k that has the property that it's 1 for k greater than or equal to 0, and 0 for k less than 0? Well, it's exactly u of k. So it seems like a kind of redundant way to express the signal. But what's important about it is what it does is it represents this signal, u of n, as a sum of time-shifted impulses where the coefficient in front of the time-shifted impulse, if it's shifted by k, is exactly the value of the signal u at k. And what we're going to see is that this will generalize and the reasoning is exactly the same. I mean, the argument we just gave, you can see this is to arbitrary x of n. We can represent an arbitrary discrete time signal as a sum of a linear combination of time-shifted impulses. And we do it exactly the same way we did it for u. We plug in x of k. And it's kind of clear why this is true, right? If you draw an arbitrary signal, here's my arbitrary signal. So it may look like this, and then hit this. Maybe I have a 0 in there. I'm not going to draw negative ones just for the sake of fitting it on the board. And so on. You know, it kind of goes on, whatever the values are. It's kind of clear that I can represent this signal. I can build it up by adding in one stem at a time. That's really what this is all about. You're adding in one stem at a time. So when you want the stem that appears at time 0, well, you better give it a scale factor which is equal to the value of the signal at time 0. And when I throw in the stem at time 1, I want to scale that unit impulse so that its height is x of 1. And so it's really just a matter of building the signal one stem at a time. That's how you can think of that. And the reason, again, this is going to be important is because when we put a signal like this through a linear time invariant system, we're going to be able to say exactly what the output of that system is by knowing only one thing. You only need to tell me one thing about that linear time invariant system, and I can tell you exactly what the output will be for every discrete time input that you put in. And that what you need to know is what the output of a unit impulse is. Because the linear time invariance is going to tell us how to go from that, which we call h of n, to an expression for the output that is produced by this general x of n. So that's why we're going to care about this kind of a formula when we talk about linear time invariant systems. And that's one reason we care about linear time invariant systems, is they have that property. You just have to make one measurement of the linear time invariant system. You put a unit impulse in and you measure what comes out. Once you have that, then somebody can come up to you and say, here, I want to put this signal x of n in there. And you can say, okay, give me a second. And you can say, here's what you're going to see when you put that in at the output. So that's why we care about these properties. So let me give you a few properties. of these impulse signals. There's one which is called the sampling property. This now has to do with what happens when you multiply a signal by, right? We can take products of signals. What happens when you multiply by delta of n? Well, if you take x of n and you multiply by delta of n, I just visualize taking an arbitrary signal and multiplying by a unit impulse. Well, that stem at 0 kind of picks out the value of x at time 0, and it zeroes everything else out. So what you end up with is you end up with x of 0 times a unit impulse. And similarly, if we multiply a signal by a time-shifted impulse, well, now the stem is sitting at time n equals n0, so that 1 is going to just pick out the value of x at that time, and then it's going to zero everything else out. So we end up with x of n0 times that time-shifted impulse. So this is called the sampling property because it kind of gives you a new signal that just sort of samples a particular value of your original signal. Then the other property, which is related, is called the sifting property. It's closely related. The sampling property has to do with taking a given signal and producing another signal by multiplying it by the unit impulse. So it's kind of, you start with x of n and you end up with another signal. In the sifting property, it kind of is related to this, but now you're actually sifting out a numerical value, the actual value of the signal, which is obtained just by using these formulas. It says if we take the product of x of n with delta of n, so we know what that looks like, and now we integrate it, so sum it from n equals minus infinity to infinity. Right, this is a new signal. This is a new signal. We could call it y of n. And now we're summing up all the values of y of n. What it does is it just, well, we're summing the values of this guy. And this guy we decided was a unit impulse, but scaled by x of 0 at time 0. So what we get out is just the value x of 0. So it sifts out the actual numerical value of the signal at time 0. And then you can do the same thing with this other formula, x of n delta of n minus n0. Again, we know what that signal looks like. It just has that one stem at time n equals 0, and if we sum from n equals minus infinity to infinity, we're just going to add up a bunch of zeros except for that one value, and we sift out the value of the signal at time n0. And then you can think about generalizations of this. If I take this signal and I sum over a different interval, not from minus infinity to infinity, but looking at maybe the sum of x of n, delta of n, maybe from n equals, a to b, two other integers. Well, what the sum is going to be determined by whether n equals 0 is in this interval or not. And you can kind of figure out, just visualize it and just kind of slide that a-b window, and you can tell what properties of a and b are going to capture that stem at 0 and which values of a and b are going to miss it. So I'll leave that to you to kind of play around with those cases. This is the representation property of the, I think of it as of the unit impulse. And it simply says that for a dt signal x of n, we can write x of n as this linear combination of time-shifted impulses, where that linear combination goes from that index of summation goes from minus infinity to infinity. Okay, and this will come in very handy when we study linear time invariant systems. LTI systems.